Over the next few lectures, I would like to talk to you about data distributions. The distribution of data plays a very important role in statistics. That's nothing new to you. You know that when you're going to conduct a test of the mean using parametric methods, you assume that the distribution of the data are normal, and if they're not normal, you have to know something about the central limit theorem, which tells you that the distribution, that the means of the sampling distribution are normal even if the distribution of the original data is not, and how quickly those data tend to be distributed normally depends upon the format of the underlying population distribution. So you have talked about distributions many times throughout your statistical career, no matter how short or long that may be. Data distributions play an important role in non-parametric statistics as well. Let's take a look at the role of data distributions in both kinds of methods. We start with this concept of a population distributional form that is always unknown. It's very unlikely that we will conduct an investigation or a research study in which we know the population distribution, but we don't know certain other characteristics such as the parameters of that population distribution. I would propose to you that seldom do we know anything specific about the population distribution. At best, we just have some general sense of what the distributional form may be. So even though you may be used to hearing that we assume some specific distributional form like a normal distribution, the fact is the population distribution, the form is unknown. What has saved us in our parametric statistics classes is knowing that even if you don't know the original population distribution, you can know something about the sampling distribution. Now, the characteristics of our inference, our statistical test, our development of confidence intervals, these characteristics actually depend upon distributional form. Even in the parametric world, if we were going to make appropriate inferences with type 1 error control, we had to know, if we didn't know the underlying population distribution, which we don't, we had to know the sample size was big enough so that the sampling distribution could be reasonably assumed to be normal and therefore give us reasonable error control. Because if it was not normal and we assumed that it was, then we would not have appropriate error control. So the characteristics of inference, power, type 1 error rate, how precise we can get our confidence intervals, those all depend upon the underlying form of this population distribution, which is unknown. So this seems like a sad state of affairs. We don't know the population distribution, but yet the inference characteristics depend on that distribution. The distributional form itself we must infer before we can proceed with inferences about specific parameters. Now there's a couple ways we can infer this distributional form. One is to actually estimate it from sample data. We could look at histograms, for example, and take a look at the shape of the histogram. Take a look at whether the data appear to be symmetrical or asymmetrical. Take a look at how thick the tails of the distribution are, whether the data are modal or bimodal. So we could look at the sample data as a way of inferring the distributional form. That might work well for quite large data sets. It does not work very well when we have small data. If we only have a small data set, then we're making an inference about this population based upon a small data that may not show us very much about the distributional form. How, for instance, are you going to look at a histogram if you have, say, 6 cases? You're not going to be able to see much about that population distribution by looking at those 6 cases. So there are some drawbacks here. Another way that can be combined with our estimation from sample data or taken separately is to infer from theoretical expectations or experience. For instance, if we create an achievement test, we may do so in a way in which we expect most of the individuals to score around some certain central value. We expect our high achievers to score above that, but not with as great a frequency. And we expect our low achievers to score below that, again, not with as great a frequency. And we can actually create a test in such a way that it's reasonable to expect that sort of distribution. We can make sure that we have questions that, for the most part, most individuals will know the answers to, but then a few questions that only our best achievers will know the answers to, and a few questions that only the lowest level achievers will miss those items. So we can, through our test development, establish a theoretical expectation for the distributional form of the data. If I was going to give a survey about people's opinion on abortion, I have a theoretical expectation, and that is that there's not going to be very many individuals in the middle, and there are going to be individuals clumped at either end in terms of their beliefs about abortion rights or the illegality or proposed illegality of abortion. So there are certain issues that are going to push people out to the extremes. There are some kinds of tests that might be created to be exceptionally easy, in which case I might expect a ceiling effect and therefore get a negative skew to the distribution. I think you get the point that there can be theoretical expectations about the distributional form without even looking at the data, and if we can combine the two, we can even have a better sense of distributional form. One thing is for certain, and that is, regardless of whether we're using theoretical expectations or whether we're looking at the sample data as a way to infer what the population might look like, general characteristics are easier to infer than the specific distribution itself. If I'm going to make an inference, it's easier for me to say something about symmetry than it is to say normality, because normality is a specific functional form. Symmetry can encompass a whole variety of forms, and it would be easier to know from theoretical expectations that I expect symmetry than that I expect normality. Similarly, when we look at estimates from sample data, symmetry can be detected before I know whether the distribution is maybe appears to be normal, or whether it really does follow that specific function that we call normal. Another property that we will be looking at when we look at distributions is whether the distribution is platykurtic or leptokurtic. Those might be new terms to you. They refer to how many of the individuals group around the middle of the distribution. In platykurtic distributions, the distribution is flat, and in leptokurtic distributions, the distributions has a very high middle. So a flat distribution in which individuals really distribute themselves across the whole range of the distribution is platykurtic. In a leptokurtic distribution, we expect more individuals in the middle. And in fact, compared to the normal distribution, we say that we have more of a leptokurtic distribution when more people cluster in the middle than what we would find in the normal distribution. But we tend towards platykurtic when fewer people cluster in the middle. This is taken hand in hand with the weight of the tails of our distribution. How many individuals are out on the ends or extremes in the distribution? We talk about having heavy tails when more people appear in the tail of the distribution than we would expect in the normal distribution. And we talk about having light tails when there are less people out in the ends of the distribution than we would see in the normal distribution. So these are all general characteristics that don't require us to specify an exact distributional form, but that we can talk about in general terms. We can talk about skewness without giving a mathematical function. But mathematical distributions have a prominent place in statistical analysis. The form of a mathematical distribution is defined by a mathematical function. That is, I can write a mathematical equation, and it is that equation that determines the form of that distribution. That equation is going to have in it parameters, and the specific distribution is defined by the parameters. So we don't talk about, for example, a normal distribution until we have specific parameters. Even with the mathematical function that forms a normal distribution, what we say is that we have normal distributions, plural. And a specific normal distribution is defined by parameters such as mean equals 0, standard deviation equals 1. If we change those parameters, then we change to a different distribution even though the mathematical function remains the same. So a mathematical function can define for us normal distributions. Specific parameters can define a normal distribution. When we have the mathematical function and the parameters, we can actually use a series of mathematical calculations to precisely know the mean, the standard deviation, the skewness, and the kurtosis. These are developed by what mathematical statisticians call moment-generating functions, with the mean being the first moment, the standard deviation based on the second moment actually being variance, and so forth. Third is related to skew, and fourth is related to kurtosis. You don't have to know about moment-generating functions in this class because this is not a mathematical statistics class, it's an applied statistics class. But what I do want you to recognize, and you already remember this from your parametric statistics days, is if you know the parameters of the distribution, you can know precisely the mean and standard deviation. So we're talking now about mathematical distributions, not about distributions of our data. The only way we can precisely know the distributions or the mean and standard deviation in our population for our data is if we assume that it has a very specific mathematical form, which is highly unlikely, nay, impossible to be the case that the population precisely follows an exact mathematical function. We use, however, these mathematical distributions to model our observed data. So we call a population of data normal in what we really might mean is normal-like. That is, the population, if we put a mathematical function of a normal curve and superimpose it on the population of data, they fit pretty well. So we're really not meaning that the population distribution is a mathematical function, but rather the mathematical function is a reasonable fit to the data we have. We use the models to observe data. Now let's talk about the use of mathematical distributions in parametric statistics and juxtapose that with how we use mathematical distributions in non-parametric statistics. In parametric statistics, we assume that the population data fit some mathematical function, that is, a mathematical distribution. Whereas in non-parametric statistics, we do not make an assumption about a fit with a mathematical distribution. In parametric statistics, then, the inference, once we have that model that models our population data, then we want to know, okay, not only is it a normal distribution, but which one? Which specific normal distribution? So we try to make inferences about parameters like the mean and standard deviation. Unfortunately, for parametric statistics, we do some crazy things in making those inferences, like, for instance, saying that we know the standard deviation, but we don't know the mean, and so we're going to make an inference about that mean. Or that we don't know the standard deviations, but we know they're equal in our two distributions that we're comparing. So those kind of inferences about parameters of distributions drive people like me crazy because they don't seem to make a lot of sense. Nonetheless, parametric statistics makes inference about parameters of specific mathematical distributions. Whereas the distributional assumptions in non-parametric statistics really relate to the kind of hypothesis that we're using. For example, we can have a hypothesis that the treatment is effective and stop there and make very few assumptions about the form of the distribution itself. On the other hand, if we want to take it a step further and say not only does the treatment help, but the mean or the median is increased by this much, then we have to make a little bit stricter assumption about the form of our distribution. But even then, we don't have to make as strict of assumptions about the precise mathematical form. We focus more on the general form, such as symmetry. In the parametric world, type 1 error control is a function of how well our model fits. So if we assume a normal distribution, but in fact the distribution's highly skewed, we may lose the ability to control type 1 error. So when we make that assumption about the mathematical fit of the distribution, we better be pretty close to being right, or we're in danger of destroying our ability to control type 1 errors. Type 1 error control in non-parametric statistics does not depend on the form of the distribution. It is, in an exact test, a given, and it's based upon the method of analysis rather than on the distributional form. So in parametric statistics, what we do is we study the so-called robustness to address how real-world distributions might influence type 1 error control. So you can find hundreds, nay thousands, of studies about how the t-test holds type 1 error when our mathematical distribution is not really a good fit to real-world data. So individuals will take data that are highly skewed, for example, or with a much greater kurtosis, or that are very lumpy-bumpy, or that are bimodal, and they'll see, if we assume that the normal distribution is the mathematical model for that real-world distribution of data, but it's really not, how is that going to influence type 1 error control? And parametric statisticians take pleasure in being able to declare a particular inference method, like the t-test, robust, meaning that even if our assumption's wrong, we still hold type 1 error pretty well. Non-parametric statisticians focus on the study of power and large sample approximations. So when we look at our method under different distributional forms, we already know the type 1 error is going to be controlled. So what I want to know is, how does power change from one distribution to another? And if I can't use an exact test, how good is the large sample approximation test of giving me nearly the same results as the exact test? Notice that in the parametric world, even if you have a robust method, that doesn't tell you how strong the power is for that method. So even if you control type 1 errors, when you have, say, severe skewness, maybe the power falls off dramatically. So what we need to do is study in the parametric world, and these studies are conducted quite regularly, not only type 1 error control, but power. And when we compare to non-parametric statistics, which does hold our type 1 error, what we need to be focusing on is a comparison of power. But notice that comparison is only really valuable if it's a comparison of power when you know that both methods are controlling type 1 error. I don't like looking at studies that compare the power of a one sample t-test to a one sample Wilcoxon test, but yet they do it under conditions in which the t-test might not be controlling type 1 error. That's not a fair comparison. To say that the power of the t-test is greater, but, oh, by the way, the type 1 error is not being controlled, is not the same as if you were to say, okay, here's a situation where the type 1 error is controlled in both. Now let's look at the power for both methods. So now let's take a look a little bit more at how mathematical models are used in non-parametric statistics. The models are used to study power and to compare methods. For instance, the sign test to the one sample Wilcoxon, or the Fisher exact test to the sign test or to the one sample Wilcoxon, or the normal scores test to the Fisher exact test. The models also provide for large sample approximations. The goal here is not to have a model that provides an approximate fit of our population data, but rather a mathematical model that will give us an approximate method that comes close to giving us the same results as an exact method would that method be available. Obviously, if exact methods are available, we should use them, but for large samples, sometimes they're not available. So we want an approximation that will give us near the same results as the exact method, and therefore control our type 1 error rates. And in non-parametric statistics, we will often use mathematical models, but we're using them to match our data to the gross model characteristics rather than the precise or specific model characteristics. So we want to say things like, all right, here's a distribution that's symmetrical. Notice that's a gross characteristic. It doesn't tell us precisely what the form of the data is. Or if we say, look, these data fit a Laplace distribution fairly well, what we're looking at is, how does the Laplace distribution compare to the normal? And we might find data that fit the Laplace better than they do the normal. So rather than going right to the normal distribution as a way of fitting our data or giving us a model for our data, we might go to another distribution based upon, again, not the precise parameters of the distribution, but the gross model characteristics, such as whether it's platykurtic or leptokurtic, whether it has heavy tails or light tails, whether it's symmetrical or skewed. And we can do this based upon theoretical expectations or sample estimates, such as looking at graphs of our data. So here are the general ideas regarding the use of mathematical models in non-parametric statistics. And in future lectures, what I'm going to do is show you some of the mathematical models that we can use. There are many, many mathematical models. I have a 3-volume set of books that is devoted to looking at all the different mathematical models that there are, all the different distributions, the uniform, the normal, the Poisson, all these different distributions. I'm going to take just 4 of them and show you 4 distributions, and those distributions will give us a good idea about how nonparametric methods will work under a variety of these characteristics that I'm referring to as gross model characteristics. So I hope you take a look at those presentations, and then that will help us understand comparisons of data sets when we're trying to decide what nonparametric method to use. So I'll look forward to talking to you more about that in later lectures.